If you think about the greatest discoveries in science, you might picture these moments of, intense pressure.
Right, like in a lab, under a deadline.
Exactly. But maybe the greatest discovery ever came from a long, quiet break from school. I'm talking about 1665.
The Great Plague.
A student named Isaac Newton had to leave his university, Cambridge, because it was shutting down for 2 years.
And he wasn't the only one sent home, of course. But what he did with that time, that was completely unique. He went back to his family's farm in Woolsthorpe,
And he was only 23.
just 23, and he already had this incredible mechanical mind. He loved building things like really precise clocks and little models.
Yeah.
But it was in that quiet, away from all the lectures, that he started to apply that precision to the entire universe.
And that's really what we're going to get into. The question that obsessed him during that time was pretty simple on the surface. Why does everything fall?
A question a child could ask.
Right. And we're going to unpack how his answer, this idea of universal gravity, managed to connect the physics of Earth with the physics of the stars. It gave us a single blueprint for everything.
For centuries, everyone just assumed that the rules for, things here on the ground were totally different from the rules for the planets and stars.
And Newton just demolished that idea.
Completely.
Okay, let's back up a little. Newton was born in 1642, went to school in a town called Grantham, then on to Cambridge. He was just soaking up math, science, everything.
He was a mind just ready to pop. And then the plague, in a way, gave him the space for it to happen. Those 2 years at home are often called his annus mirabilis, his year of wonders.
Even though it was 2 years.
Right. And it was there that he wasn't just observing the world, he was questioning everything. Like, why do things start moving? And why do they stop?
Which brings us to probably the most famous story in all of science.
The apple.
The falling apple. And look, the story might be a little embellished, but the core idea is what matters. The big insight wasn't just seeing an apple fall.
No, people had seen that forever.
The brilliant part was him thinking that the same force that pulled that apple down to the ground could keep going outward.
That is the revolutionary leap. He literally asked himself, if the force reaches the top of a tree, why wouldn't it reach the top of a mountain?
And if it reaches the mountain?
Why couldn't it reach all the way to the moon? He realized gravity wasn't just some local thing here on Earth. It was universal. It connected everything.
It's just mind-blowing that he made that connection then, while everyone else was just trying to survive. But let's talk about that word universal. Before we get to the moon, we need to be clear on how he actually defined this invisible force.
Okay, so we all use the word gravity.
Yeah.
But Newton defined it with two really specific things. At its core, gravity is this invisible pull between all objects that have mass.
So it's a property of matter itself.
Exactly.
Mm.
And how strong that pull is depends on just two things: how much mass the objects have and how far apart they are.
All right, so let's break down the mass part first. This is why the Earth's gravity is such a big deal for us, right?
Precisely. If you want a strong gravitational pull, you need a lot of mass, a lot of stuff. Earth pulls on us so hard because it's gigantic. Your water bottle technically has gravity, but you'd never feel it.
Because its mass is just tiny compared to the planet.
It's insignificant.
Now, this is a really critical point. We have to separate two words that people mix up all the time: mass and weight.
Yes, this is so fundamental. Mass is the amount of actual matter, the atoms that make you up. Your mass is your mass. It doesn't change if you're on Earth, the moon, or floating in deep space.
But your weight absolutely changes. Weight is just what gravity is doing to your mass.
That's it. Weight is the measurement of gravity's pull on that mass. So if
Okay.
you're on the moon, which is much smaller than Earth, it has a much weaker pull,
So you'd weigh less.
a lot less. Someone who weighs 150 pounds here would only weigh about 25 pounds on the moon. Their weight plummets, but their mass, the amount of stuff they're made of, is exactly the same.
That's a huge distinction. And Newton didn't just stop with mass. He had to figure out a rule for how this force works over huge distances. How does it get weaker?
And this is where his, clock-making mind really shines. He came up with a mathematical rule called the inverse square law.
It sounds complicated.
But the idea is pretty simple. It just describes how gravity weakens with distance. And the key is that it gets weaker very, very quickly.
It's not like you move a mile away and it's a little bit weaker.
No, it's not linear at all. Think of it like a flashlight. If you shine it on a wall from 1 foot away, you get a bright circle of light.
Okay.
Now move 2 feet away, you've doubled the distance. The light isn't just half as bright. That same amount of light is now spread out over an area that's 4 times bigger, so it's 4 times less intense.
Ah, I see. So if you double the distance between, say, the Earth and the Moon.
The gravitational pull between them becomes 4 times weaker.
Not 2 times, 4 times.
Exactly. Triple the distance, and the force is 9 times weaker. Quadruple it, and it's 16 times weaker. It drops off by the square of the distance.
And that explains why the sun, which is unbelievably massive, doesn't just rip us off the surface of the Earth.
Right. It's so far away that the inverse square law cuts its pull way, way down, letting Earth's gravity be the one we feel.
So what Newton basically did was hand scientists a calculator for the solar system. He made the movement of planets predictable.
He did. It all came together in his huge work, the Principia, the law of universal gravitation. It states that every piece of mass attracts every other piece of mass in the universe with a force you can actually calculate.
It tied physics and astronomy together. One single law.
A total game changer.
So let's talk about the consequences of that law. The most obvious one is maybe orbits. Why does the moon go around us instead of just crashing into us?
It's this perfect balance. The moon is, in fact, always falling toward the Earth. Our gravity is constantly pulling it in.
So if it just stopped moving sideways, it would fall straight down.
Absolutely.
Yeah.
But it's also moving forward at a very, very high speed. It has this huge forward momentum. So as it falls, it also moves sideways, and it always misses.
It's constantly falling, but never hitting its target.
Exactly. That combination of falling toward Earth while moving forward creates that curved path we call an orbit. It's a perpetual dance.
And that same pull affects things much closer to us, like the oceans, the tides.
Tides are a direct result of the moon's gravity stretching the Earth.
Sure.
The moon pulls on everything, the land, the water, but water is a fluid, so it moves the most.
So you get a high tide on the side of the Earth facing the moon because the water is being pulled toward it.
Right.
But why is there also a high tide on the opposite side of the Earth at the same time?
Ah, that's the cool part. It's the stretching effect. The moon's gravity is actually pulling the solid Earth slightly away from the water on the far side.
So it's pulling the planet out from under the water in a way.
You can think of it like that. It leaves a bulge of water behind, so you get 2 high tides at the same time. The sun does this too, but it's so far away its effect is only about half as strong.
And then if we zoom out to the whole solar system, this is what governs everything.
It's all about the sun's dominance. The sun is 99.8% of all the mass in the solar system. Its gravity is just overwhelming.
It locks all the planets into these stable orbits.
And it's why planets closer to the sun, like Mercury, have to move so incredibly fast. They need that speed to fight the sun's stronger pull and stay in orbit.
Newton turned the solar system from a mystery into, like you said, a giant clock, a predictable machine.
The universe suddenly made sense. It followed rules.
Yeah.
Mathematical rules.
And these laws really are universal. They apply to every planet, every moon.
Absolutely. You can use them to figure out what gravity would be like anywhere. If you went to Jupiter, which is huge, you'd feel a crushing gravity. You'd weigh hundreds of pounds more.
And on Mars.
Much weaker. You could jump way higher than you ever could here. Newton's laws let us calculate that perfectly.
And it's amazing that we still use his math today for every single space mission.
It's the absolute foundation. Engineers use his laws to calculate exactly how fast a rocket needs to go to escape Earth's gravity.
Escape velocity.
Right. And they use the inverse square law to plot the path for a rover to land on another world. It's all Newton.
It's not just space either. It's engineering right here on the ground.
Every day, if you're building a skyscraper or a bridge or designing an airplane, you are working with and against the force of gravity. All of it relies on understanding how mass attracts mass.
Newton basically proved that the universe runs on logical mathematical laws that we can actually understand. He changed the world from a place of mystery to a place of logic.
He really did. His work is the foundation for almost all of modern physics.
So at the end of the day, his laws of gravity explain everything from the tides to how entire galaxies stay together. He saw an apple fall and turned it into a mathematical truth for the cosmos.
It's the universal glue. The same force that keeps your feet planted on the ground is the one holding a galaxy of 1 billion stars in a spiral. Something to think about.
Good luck with your studies.